models there. One of them will be called the hybrid budding model, and I'll see if I can show this to you interactively, just so you can get a sense of what I'm talking about. So we'll go over here to bootcamp and incubator, participant resources. Here we go, example models, and I'll get this. I'll start that in just a minute. And then there's a thing, if we sort by name, there should be a thing called hybrid models. Hybrid models here. By the way, if any of you just see icons rather than these names, there's typically a thing you can kind of fob up here in the left to turn it into a list of names, which would let you see them in greater detail. Ooh, okay, I did something bad. Okay, there we are. Hybrid models, and then we're going to go here to one that's called budding hybrid, SDABM. Do you see that? Remember, if you click on it, okay, in this case it actually goes in there, and I don't know why it's graying it out, but if you click on that, you should have a download button that's like a downward facing arrow, and again you push that. Okay. Similarly, I'd like you to download, so that's budding hybrid. You could just download it for now. I'd like you to download CTL state variable, use AnyLogic 7. Okay. They said about Newton, one recognizes the lion by his claw. Jeff might know the Latin for it. And from the way these models are named, I kind of know the student who was involved in last frobbing them.
So that one has several files or something?
Yeah, thank you. Most of them are extraneous. They're like pictures of, they're pictures of sort of pathogens. Just CTL state, just the ALP files is needed. Yeah. Another one that I'd like you to download would be this one. It's called Environmental Contamination Hybrid. Okay. Environmental Contamination Hybrid. I'd like you to get that. That's a goodie. Another one would be Gridded System Dynamics V8. Okay. And another one would be Multi-Clinic SIS Hybrid Saturation Effects and Lock-in. Okay. Sorry? Multi-Clinic SIS Hybrid Saturation Effects and Lock-in. Okay, could someone help Kate?
I got it.
Got it? Okay. Okay. I think that's pretty good set. Maybe I'll get one more called Basic Health Economics, ABM. Okay. That's probably worth a glimpse.
So there's 3 versions of that?
Oh, in the folder?
Yeah.
Oh, yeah, you just want the one with the shorter name, if it can be called such. Basic Health Economics, ABM, AnyLogic 7.ALP. Don't take the refactored one. That should have been refactored, but yeah, the other one is original. Okay. Great. Okay, so Anyone needed to check any of those with me, like clarifications and which ones? Okay, great. So we're cooking with gas. We just downloaded those models from the site, and anyone listening in from the internet should realize there's a repository of my of my models on the internet that I'll try to make sure include all of those. Okay. So within this, I should start up the recording here. Okay, and this is hybrid modeling. Hybrid modeling, compelling patterns. And here we go. And we will do highest display. Okay, great. Okay, it's firing up, and here we go. Great. Okay, it's about, okay, great. So, in this talk, I'm going to present to you 5 compelling patterns, or 5 types of hybrid models that I consider really compelling in terms of their value proposition. And we're going to look at them in a hands-on fashion. And we are, moreover, going to talk about some of their implications. So the opening reflection here, which is something that in which I've expressed conviction elsewhere in the camp, is that system science methodologies are highly complementary. In a world of too much tribalism, all sorts of things, system science area is no exception. Any very tightly clustered communities that feel comfortable only in a particular area of formal training, and often they misunderstand the goals and also the kind of essential elements and building blocks of other techniques. Don't really understand where they fit in, and often disparage them as a result. It's more than my conviction. It's my observation over decades of having worked with multiple types of techniques. A little bit unusual because I started my H&based modeling 26 years ago in 1990, and then I started running a firm doing predominantly system dynamics consulting in 1993 in short order, and this has given me sort of decades to sort of think about the trade-offs between these methodologies, and to think at least that I'm being less biased to the table than besets many in the field in terms of the trade-offs, and much more than when I use one technique to the other, for the simple reason I need to deliver, and we're trying to figure out what's the best match. I think Jeff has been in a similar situation, and both of us have at times been ostracized or otherwise sort of squeezed by different communities who dislike other types of models, which is an odd sociological phenomenon. So different methodologies seek to answer different types of questions often, and often use different formalisms, different ways of representing, the dynamics of these dynamics. That, well, at a technical level, anything you can do in one, yes, technically you can do with the other. It involves such such a infeasible, or at least such a remarkably greater amount of work to do it in one than the other that it's not even contemplating. And system science methodology, I view sort of having its own core area of where it shines. It just does spectacular, and there's no one of them that eclipses the others, despite heediness to this effect. And significant synergies can be secured by using combinations of them to address the same problem. Now, a few motivations for this. It may seem to you obvious given that statement, but it goes deeper than that. So it is true that each of them has comparative advantage. So if I'm going to have a presentation of a population health issue which involves contact with care processes, which involves contact with clinicians or so primary care doctors or specialists or or contact indeed with surgery for drug addictions or what have you, smokers, etc. It may be that having represented with agents and that care process represented with discrete event models is very natural. And that's what I call comparative. Age-based model, you bet. It would just take a lot more time and it'll be a lot more buggy, and that time has costs. It takes you away from other insights. Secondly, there's different analysis needs in different areas of the model. Our questions about this area might involve service delivery type questions, health service research type questions. Our questions elsewhere in the model might focus more on sort of broad population outcomes. And because of that, having one size fits all can be sometimes problematic. I think one of the most important features, though, motivating hybrid modeling is this issue of adaptivity. The fact is, I presented to you on the first day, and I've reiterated many times, and I will do so again today, that modeling projects are learning opportunities. And modeling, I believe, use of dynamic models it reaches the greatest of its potential when we use them as learning tools, not as crystal balls, but as tools to refine our thinking, to learn more quickly and deeply and robustly from empirical evidence, and to incorporate that in our understanding. And the issue is that often you learn a lot in the modeling process that shapes your understanding of what the model needs to look like. And the fact that you can advance a modeling project in system dynamics for a while, purely aggregate system dynamics, and then you realize we need to represent this area of the model in greater detail. We need to expand this area to represent detailed agent histories and perhaps networks, and to situate people at locations and geographic space. Or we need to change it so we can have situated decision making on the part of the agent based on their preferences. The fact that we can take that aggregate model, and then just carve off a piece of it which is agent based and still interface with the aggregate model is very important, because it lets us capitalize on our learning without throwing away the original project. It lets us weave in to certain areas of the project our needs without throwing out the baby with the bathwater. We don't have to re-implement it all in agent-based just because we think a portion of it has to be captured in agent-based based on our learning of what it's sensitive to, or learning about the dynamics as motivating representation of certain causal pathways or interventions based on a person's history or what have you. So this ability to change the boundary of the model as to what's represented in more detail, less, what's endogenous, what's exogenous, that's a big motivator for me for hybrid modeling. Stakeholder resonance is another issue. We need to appeal sometimes to stakeholders associated with certain regions of the model. Jeff speaks a lot about this as an MD himself, and as someone who's dealt with MDs in a variety of capacities. He long articulated for me. I remember utterances to this effect probably 6 or 7 years ago, commenting that when you're dealing with clinicians, often what they gravitate towards, what they understand is individual level depiction, because they're used to dealing with particular patients. Their world revolves around particular clinical encounters and patients, and so when you show a stock and flow diagram with broad categories of people, they will sometimes tone out. It's just too high level of abstraction. They can't relate it to their direct experience. Conversely, you work with demographers who are very used to segmenting the population, stratifying it into different groups. And I've been told by demographers, at least there's a group of them that feel extremely comfortable and feel most natural in a high-level aggregate system dynamics depiction. There are people who are working in clinics who will just immediately get discrete event modeling because it maps to some of their other informal mapping methodologies. So different stakeholders will often resonate with different formalisms. And in as much as you need to secure credibility, buy-in, ongoing involvement by these stakeholders, using a type of modeling to which they can relate and which can therefore be used to elicit their knowledge, their understanding, rather than having them tone out, is not a small matter. It's not merely, sort of accommodating in a grudging way their desired representation. In fact, it may mean the difference between a model that goes nowhere and a model that succeeds. The fact that you're going to be able to get them to look at it, understand, and therefore critique. Ladies and gentlemen, and this doesn't belong here, but I have nowhere else to put it. For me, it was a big aha when I realized. It's amazing. You would think when you start a modeling project, you should be able to sit down with stakeholders and talk with them about the evidence base and have them bring forward areas of evidence from their direct experience relevant to the model. Sit down, do a thorough sort of cataloging and inventory of what's known and what data sources are available of their own experience for expert guesses at certain parameters, and take that off and have the model built on that. But the world is not so neat. And it's the same thing over in software development, which I've also been doing for decades. Before I was a modeler, as a professional software developer. And depending on who you talk to, they think I've either gone to the dark side or the light side. Ladies and gentlemen, there too, there's this nice idea that we sit down with stakeholders and say, tell us about the IT system you want. And they sort of say, well, we need to do this. We need a screen that looks like this. We need some way of doing this. And you could have that conversation. You go off and you build the system and you deliver it to them and they're happy campers. They're not. You do it that way. It's called the waterfall model, and it's a recipe for disaster. Probably you'll show them the system and say, that's not what I want. That doesn't meet my needs. And so what you do instead there, and what we do in modeling now, is we try to get them seeing the model as it develops, because the key thing is a lot of their tacit knowledge about the system won't be elicited until they actually see it. It's until you're running it in front of them and they see patterns and say, that's just what I saw. I've never mentioned it to you, but that's actually what I see in the clinic. Or they'll see something, they'll say, nah, I never see that. That's way too high. And why they didn't mention that up front? Well, because we're human. We have a lot of tacit knowledge that doesn't, I was going to say twig, but that's not the right word. It doesn't sort of get activated until actually we see something very concrete in front of us. And having those abstract discussions about knowledge is great, and I'm not saying don't do it. It's just that often you need to show them an actual concrete thing. That's when they actually get it, and that's what motivates them. But more than that, that's what elicits points of knowledge from them. That's what actually brings out observations that otherwise lay hidden. And there's something really important to that. So this issue of stakeholder resonance, it's not merely a matter of firing them up. Often it's a matter of getting credible understanding elicited from them about the system. And you need to have them face concretes that they're familiar with, which they're familiar. Okay. Greater computational efficiency. It turns out that a big agent-based model of the U.S. population that simulates it at scale in terms of number of people is a very, very large computation, exhibits very large computational burdens. It imposes large computational burdens. And often, as we'll see, we might be able to get by with a model that's 80% of the population is aggregate, and only 20% is captured at an individual level. And we've reduced hugely the issues. I have a colleague in the States who confided to me that she does discrete event modeling, and they're doing some great work with clinical care processes with discrete event modeling. But they're trying to do it at scale with, millions of people in the model. And she spends most of her time, it seems, bogged down in, running these computations on large clusters, and it's all very long between when you modify the model and you actually get results, and it's really slowed down that learning loop for her. And so this issue of sort of the computational efficiency is also not a small matter. We learn best when we have a quick learning cycle, and system dynamics is very good for this traditionally with simpler models, with aggregate models. That's not the only way we use system dynamics, but when you have that, you can run them interactively and kind of explore insights that come up, whereas a really large-scale model can be challenging, and one has to plan for it. The point is, by hybrid modeling, we can actually secure economies there. And then multi-scale modeling, where we have different types of processes at different level. Maybe we have system dynamics at a high level for the policy regimes and the kind of response to the healthcare system, and then at an individual level we have agents. Or maybe we have discrete event modeling partway up to capture the service deliveries. We have agents with system dynamics within them, and then at a high level we have some features of kind of agents representing, additionally representing the institutions or non-state actors, etc. So we're going to talk about 5 compelling hybrid modeling patterns. A pattern where we have service and population interaction. So we have a population represented with service processes taking place on the population, such as meetings with a clinician or meetings with the emergency department, etc. Case where we have an aggregate population that's represented in a rough and ready way in a stratified aggregate model that allows you to abstract away from all sorts of vagaries of individual behavior. And then you have an at-risk population or high-risk population that's individuated, meaning turned into agents. You couple them together. And you might have flows back, well, you will have flows typically back and forth. Someone goes from the aggregate population, becomes at risk, they turn into an agent. We call that budding, based on a chance remark in a different area by Sandro Galea, and then you might have people flowing back the other way, as was built in this very boot camp a couple iterations ago by Jeff and Robin and others. System dynamics driving agent evolution. This is a really important one where you have system dynamics to capture immune state or strength of belief or level of risk perception or level of stress. In short, you have it capturing continuous dynamics within an agent, particularly for regulatory processes where there's feedbacks involved within an agent. Agents driving aggregate system dynamics, we'll see that with a health economics model, but we'll see it elsewhere as well. And then aggregate system dynamics drives an agent population. So we have sort of environments, perhaps with pathogen built up, which can affect agents. So let's talk about this. This service population interaction. We have some papers along these lines. The idea here is we have some catchment population, for example, for a service facility. These are individuals in the population who exhibit all the fruits of agenthood. So they can be arranged in networks, they can have geographic location, their individual histories can be maintained, they can have individuated, situated decision making, lots of good things. But when they exhibit certain health needs or other social needs, they present for care associated with care delivery processes. And those care delivery processes are simulated by a resource-constrained representation of these service processes, which may be spatially explicit. Here you see people coming in, being hived off to different rooms. Here's a bunch of residents here, and there's a senior clinician who's doing the history, physical, and diagnosis there. And so people come in, they're treated by these people in the facility, and then they leave. To illustrate this, I would like you, ladies and gentlemen, to load up to which that multi-clinic model that I mentioned earlier. So I'm going to close all my models, of which I enjoy a few. And I will now go and open up the multi-clinic model. Okay, we are caused by slowness here. Okay, okay. So what's going on? Okay, so okay, good. And now I'm going to open up. Okay, and we're going to go to classes, consensus, examples, any logic, 7 examples, hybrid, boom. Okay, and we're going to open up this multi-clinic SIS hybrid saturation effects and lock-in. Do you have that? Okay, take that as a yes. Great. So ladies and gentlemen, I delivered a boot camp. I'll keep that a secret at a major university in February, and we had a bunch of keeners in the room. That's Canadian sort of people who are really keen to learn, and one of the guys was really nice guy. He was kind of quiet, but he would and he seemed to really be following everything remarkably well, just like many of you folks here. And then on the last day of the boot camp, over lunch, he said, and we were talking how long I've been teaching boot camps, whatever. He said, so do you have any people who, like, during the boot camp, they just, like, totally lose it? They freak out and they can't take it anymore and they run out of the room and they just wig out because they can't stand they can't stand the intensity of it. I said, no, should I be worried about that? sort of thing. So thank you for your tolerance, ladies and gentlemen. Both of my humor and of the intensity of said boot camp. Okay, so let's take a look at this model. What do we got here? Let's go to Maine. Let's go down Maine, and here in Maine, 3 populations: one of clinics, one of people, and one of homes. Okay, and not surprisingly, just as in yesterday's model, if we go to person here, each person is associated with a home. Okay, they're also associated with a sex and an income. And notice that they exhibit a natural history of infection with respect to some infection, and they exhibit a care-seeking process. Do you see that? See that care-seeking? Okay. Now this care-seeking process, what do you think we would see? What do you think that? See this little transition here? What do you think that's? At what do you think that's aimed? What do you think the job of this transition is? Yeah, it updates the hazard rate. It updates this I thought it was that hazard. Maybe I'm wrong. Okay, let's go check it out. Re-examine condition. This is the fox has shown its tail. Okay, yeah. So the deal is this transition. In this case, actually, the rate doesn't need to be updated, but what does need to be updated is what's called the guard on that rate. This transition is only eligible if this thing is true. Often we use that to like guard against men becoming pregnant, which we generally want to avoid. So in our models, we might have a guard saying, the pregnancy transition for an individual is only available to women. Here, we're actually gating this according to their state in this other state chart. And we're only saying, okay, when they're in the this infective and symptomatic state, that they will make this transition. So we actually sort of leave and come back in so we can re-examine that guard. Okay? Now, when this happens, what do you think happens in this transition, or would happen in the entry to this transition? What do you, based on yesterday, is going to happen there? If this is an in-transit state, you notice there's an arrival here. What do you think we start doing here? We get them, what? Moving. Here's this move to. See that? They move to the clinic. Okay? And then then they get to the clinic. They arrive for care here. And notice when they arrive for care, this is like the essence. This is like the key nexus of the model. One of the key nexuses, probably this is the single most important. When I arrive, I tell the clinic, take me in as a walk-in. Take me, this is me, right, this. And as a walk-in patient in this clinic. Okay, so I've arrived at this clinic. Note that it's the nearest clinic, okay? Nearest clinic, which is going to be computed, as I recall. I've got to check this. Notice nearest is determined right here. When they about to start moving, we say get nearest agent from all the clinics. See that? We get the nearest clinic to me. We save it in this variable called nearest clinic. Given that we have three types of agents, a person, home, and clinic, what sort of variable do you think this would be? A reference to a instance of clinic. It's a clinic, right? And so here we determined what the nearest clinic is. We start moving to it. And when we arrive, ladies and gentlemen, when we arrive in this clinic, we ask that clinic take us in. Let's go look at that clinic, okay? Here we go. So here is that walk-in thing. We asked to join this walk-in for our destination clinic. We came in here. And this clinic, I know we haven't spent time on this event model, but what this is basically a queue of people. They're awaiting treatment. Jeff likes to sort of combine these two in what's called a service block. I like to break them out because I think of them conceptually separate. This is a queue. This is a bulking transition. If they remain in that queue for too long, they will bulk. They will leave the queue. Jeff says in Australia they wouldn't call it bulking. They call it leave without being seen. But you'll notice that in this queue, if we scroll down, I think it's under advanced now. Yes, under advanced. Look at that. This should be checked. Enable exit on timeout, and we should specify a timeout. We could draw it from a random distribution, from a distribution, or we could make it based on the agent's characteristics, if their condition. We could have any bulking time, bulking thresholds be determined for that agent. If they continue on for treatment, then something happens, and this is the next nexus, which has it's consonant, but it has an awkward ring to it. The next is right here. So they undergo treatment, ladies and gentlemen, and that takes some time. This is, again, a little workflow for this clinic. It takes between 0.5 and 1.5 hours. Okay? We could easily make it depend on their characteristics. And then watch this. Here in this successful treatment, there's a certain probability of treatment success. Clearly, we could make that depend on the agent's severity, their CTAS levels, or what have you, their acuity level. But depending on this, right now it just flips it. In general, we can make it much more sophisticated. You'll note there's two options: successful treatment and treatment failure. Now, you may wonder, why are we distinguishing those? Those both go to this thing here where we are releasing a healthcare worker. I should have noted, this is I stand remiss, I sit remiss. This is a queue where we're waiting for a healthcare worker to be allocated to us. So if there's more healthcare workers, we'll typically get out of the queue sooner. On the other hand, if there's fewer healthcare workers, we'll be waiting here longer, right? We're waiting for that single nurse and there's 20 other people online ahead of us, right? This is where they're released. So why do we have two paths here? There's the rub. Go this. And now I'd like you to go open up a part that was previously hidden. It's under actions. And you could see what happens here. When they leave via the true mechanism, they're sent a cured message. I had forgotten this model has a rather blunt depiction of illness. And this individual is sent a message that simply says cured. In other models, well, I've got to relate it, Jeff. In other models, we haven't even had a limited number of healthcare workers, just to do it quickly in a boot camp. We've just had people go to the clinic and they undergo treatment and come back. And Jeff has noted that it's as if they have to walk through a beam, a healing beam, in the treatment, and they leave. I think that caused me adverse laughing reactions in Adelaide when he proposed that our clinic representation was actually not too simplistic if you think about it as being beam-mediated treatment rather than human. If they simply walk through a beam and they're cured, that's probably not a bad representation if we don't have a limited pool of healthcare workers. Okay, so back to business. This sending, you'll notice this key thing here, ladies and gentlemen. We send a cured message to the agent. Notice the self here refers to the agent, okay? So they're flowing through here. Some of them balk. They come through the treatment. If they are successfully imparted care, they are then sent this message cured. And now, this is the key other nexus, okay? So if we go to person here, where do you think the cured message would be received? Does anyone want to hazard a guess? Where would that cured message bring them? Yeah, it's in the infection state chart. And from what state to what state? I'll give you a hint. They only present for care if they're symptomatic. So, back to susceptible. So let's go look at that transition here. And you notice that they will go back to susceptible if they receive the message cured. Okay? This model and depiction of being curing has received several remarks by clinicians who also felt it was a little bit abstract. But the point is that the care process renders them treatment which can lead to a relief from affliction. Okay? So here they're sent a cured message, and here when they receive that cured message, they'll go back. Note in the clinic that if they exhibit treatment failure, if they encounter treatment failure, there's no message sent to them. In other words, what do you think would happen at the person level then? if no message is sent to them, where will they remain? In the symptomatic state. That's right. And that will motivate representation. That will. So they'll actually go back. You notice this here. This is actually based on when they receive a message. It's unconditionally when they receive a message, they're going to go home. Excuse me. It is based on a message. Okay, this is interesting. They depart the clinic here. I just got to check this because they should have left the clinic one way or the other. Normally, we send a message departed clinic here. And so if they received the departed clinic message, really that person one, okay, I should fix this should be contingent on the departed clinic message. There we go. On a particular message, departed clinic. That's when they return home. So a person who's ill and who has not obtained relief from their afflictions, they are going to return back when they're done with the clinic to not seeking care. They'll simply represent quickly because they will remain in this infective and symptomatic state. They'll be, when they come into this, they'll have this certain hazard per day of representing because they remain in the state. On the other hand, someone who was cured, in fact, when they come in, this guard will be false. They're no longer going to be in the infective and symptomatic state. It'll be false, and therefore they won't get to this point. Okay? They won't actually enter this state. They won't, in fact, transition across here because they're simply not ill. Okay, so that is a very stylized representation, but it harks to this basic underlying principle that we can represent individuals in a population presenting for care at a clinic when they are ill, based on their state. They remain a population while they're in this clinic, but their progression is affected by their treatment. And so if they receive successful treatment, they will be cured. Now, neither the beam idea nor this one relates to a particularly key element here, which we could have this provision of treatment, for example, that the quality of care conferred could be in fact based on the level of busyness of the clinic. How many people are waiting, for example. Maybe with lots of people waiting for care, the clinician feels pressure to finish up an appointment sooner. So maybe the appointment is quicker on the one hand, but there's lower probability of successful treatment on the other. In which case that individual may be released back. It'll be sort of penny-wise pound foolish. It'll look like a fix that fails where they actually go back home, but they're coming back. So the clinician thinks they've accomplished something. They've got through this patient, but the patient comes back the next day more ill than ever. And we could easily capture that in here. But this was a little example we built up in a boot camp, and we didn't go into it extra detail. Another thing that could be accomplished here is having success depend on the patient's status, the patient's level of complexity, on the physician experience, etc. We could also naturally have more than one type of resource that's needed. Maybe we have nurses that are needed for certain types of stages of the process, physicians for others, rooms for other cases or pieces of diagnostic equipment. All of that is readily doable within the confines of discrete event modeling. The essential feature here is the hybrid character. People present for care, ladies and gentlemen, at clinics. They start moving, they find a clinic, they start moving to it, they arrive at a clinic, they join the clinic in terms of the set of, and then their health trajectory is then affected by the clinic's operation. Okay? So that's one hybrid model. I hope you appreciate the significance. This could be clinics. It could be service, service associated with allied health professionals, social workers, occupational therapists. It could be service processes for, for getting registered as disabled by the Veterans Administration in the U.S. It could be all sorts of things. The key point is we can use the right tools for the right job. Representing the population, we can have rich depiction of individuals, their history, their social networks, their location and geography, etc. And then for representation in the clinic, we can use the exquisite tools of discrete event modeling to capture resource-limited workflow in a rich way with an economy of mechanism. Yes, sir.
You had mentioned that the first queue, the allocated healthcare worker,
Yep.
was supposed to have something put under advance for enable exit on timeout. Is that true?
So yeah, this one here. So this one, for reasons that are mysterious to me, we actually had a timeout transition, but when I went and looked on it, enable exit on timeout was not in fact filled in, and it may be that I disabled that during the boot camp to show people what the difference is if, in terms of queue length, if there's no timeout. Generally, for the timeout here, we wouldn't have a fixed value. We draw it from a distribution, or you'd make it based on patient characteristics like their severity. So someone, who's been terribly injured is not going to walk away. Where one time my wife's an MD, and she, I went to I was curling, and I fell, and I thought I might have broken my elbow, and I went to the clinic. And she told me, she said, I went to the emergency room. She said, don't go to the emergency room. They're going to laugh at you. You kidding? You come in there with your hurt elbow? She said, you're going to just wait. And I said, well, I want to go. Just in case, maybe it's broken. And she said, okay, you can go. I think we went together. She kind of came along with me. So we went there, and they took a look at me, talked with me about my elbow hurt during curling, and then said, okay, you can wait here. We'll tell you when a physician's available. And the hours passed, and my laptop battery got lower and lower, and people were coughing all around me, and people were being brought in on stretchers from car accidents and being seen immediately, and the occasional person was taken from the waiting room, and people were coughing more, and kids were crying, and time was going on, and my laptop ran out of power, and I said, well, maybe my elbow's going to heal anyway. I couldn't feel anything, quite off about it, except that it really hurt. And so we went home. And she's reminded me of it on one or two occasions since then. So we exhibited timeout. I exhibited what I would call balking, but Jeff, I left without being seen.
Did not wait.
Sorry?
Did not wait.
Oh, did not wait. Did not wait.
No,
Okay.
left without being seen is Canadian, isn't it, William?
Yeah.
Yeah.
Le-
You say DMW, did not wait.
Oh, is there in Canada too?
No, yeah, Canada's our.
We use left without being.
Left without being
That's
seen.
Canadian.
Okay. Yeah.
Australia did not wait.
Okay. Yeah. Okay. Anyway, very important type of hybrid modeling. I think it's just so sweet. Okay. So let's close that. Let's go on to the next type. Any questions about that type? Okay. Boom. Any questions about that type of model? Okay. Ladies and gentlemen, we build a lot of example models in the Start incubators, just pure boots. We like clinic level model. Okay, the next thing I'd like to talk about is the issue of this issue of a zoomable population. A zoomable model in the regions of it are articulated at a greater level of detail. The idea here is that we're going to have a coarse view of part of the population, and typically most of the population. And we're going to have a very detailed view of a small number of individuals, okay? Where the small number of individuals are focal population interests within our. So in order to to open this, we're going to go and we're going to open a model that is called budding hybrid SDM model. Okay. Now, this model is like the previous one, decidedly simplistic. I often build this with less than an hour, but it is a basic principle. So we're going to have a general population, we're going to have an at-risk population, and then we're going to have a population of focal interest. And the idea is that people get individuated here. Here they're just numbers in a stock. And don't get me wrong, the general population may be stratified by age and sex and ethnicity. It's not that this has to be some undifferentiated whole for the entire population. Not at all. We may actually break out subgroups of greatest interest, but the point is that it's not represented at an individual level. So it may be a fairly rich aggregate representation from a stratification standpoint, but the point is that once individuals reach a certain point in their progression, they will be individuated as agents. Okay. Now, why would you do this? Well, there's a couple key features of this. Number one, we can have a tighter focus for our individual level investigations. We can focus on the individual behavior, characteristics of, location, decision-making processes, all the features of a population of greatest interest, but we can still represent the population that gives rise to them very readily. An example would be those with cerebral palsy who develop it later in life. There's a broader population who's at risk of cerebral palsy, but we don't have to represent all of them at an individual level until they get to a certain point in their clinical continuum. So this would be an agent population represented at detail, and this is a population represented at a coarser level because our focus is not there. You can have much lighter weight simulation. You're going from a situation where you might have 10,000 agents in the model from a situation where you might have 1 million agents in a model. It makes a big difference. And as a result, you get faster experimentation and speedier insight. So we've used this for a number of our projects with great success. Jeff has further with, remember Robin's last name? Robin? Clay Williams, thank you. They did a very nice little model of service delivery in a hospital where basically we had individuals who were captured at an aggregate level, and then at some point they were individuated, and then after a certain point they flowed back into an aggregate representation. So it's not like once an agent, always an agent. Sometimes you want that because you want to trace their history, back, but sometimes after after their elbow has been healed, or after some point in their clinical encounter, you want them to be represented at an aggregate level again. You're not as interested in following them. So let's just check this out briefly, okay? So this is a very crude model, and again, we could build it in about half an hour or so. But here we have a stock and flow model. We have non-diabetics, and then they have a mean time to develop diabetes. Again, don't get distracted by the fact this only has one stock. The whole thing could be a big system dynamics model, stratified by age, sex, ethnicity, and quite rich. But the point is, it's not an individual-based representation, so we can't capture network structure. We can't capture features associated with an individual's history and decision-making and interventions based on that history. We're not capturing their spatial location. We're not able to really richly capture their situated decision-making. So we might have a very rich agent system dynamics model, but at some point these agents transition across a key flow, and they get placed in a stock of people in waiting. Okay, and these are sort of waiting up to be queued as agents, and then periodically, whenever this thing goes above 1, we'll go and create an agent. And what happens when we create an agent? Well, basically we go through and we add each one to be created to the population. We debit the number here from that one that we created, and we basically set this to trigger off again when this goes above 1. So basically, if there's anyone waiting to become an agent because they've transitioned down a key sort of flow, they become an agent. They get turned into an agent very quickly, almost immediately. As soon as there's a person waiting to become an agent, they become one. If there's no one waiting to become an agent, the system dynamics population is just continuing on. It'll keep on accumulating here until this goes above 1, and they become an agent. So you can run this. Should have run that last model, but time is of essence. You can learn a little bit from the dynamics, perhaps more about how they work. Okay. Bad. Okay. Okay. So here we go. Great. So here we go. So what's happening is these agents start here, 1,000 of them, transition down here, and as soon as they kind of go across this transition, they get turned into one of these agents. So these agents are people in this agent population. You notice 80 of them, 90 now have been created, and they've been created by virtue of having left here and been created here. So don't get distracted by the overly small version of this. The point is that we can represent part of the model at an aggregate level and have the very individuals who were there get turned into individual agents if they reach a certain point in the model. Okay? So here we are having people individuated in ways that we can follow their individual characteristics. But often most of the model is still in stock and flow. It's a sweet combination. It's a svelte combination. It's kind of low overhead. It lets you put your modeling effort to where you feel it really matters, and lets you go kind of in a broad brush set of strokes for the broader population who is of less central interest, but still capturing the fact they can develop risk factors and can reach a point of being of focal interest. Okay? Simple little model, simple design. You could copy it and use it in much more sophisticated system dynamics models and get the agents to be created at a point of interest to you. Okay? Okay, ladies and gentlemen, this one is a fun one. Open up a CTL state variable, use any logic 7. And your model will look, so where did I get that? Same folder, CTL state variable, use logic 7. This, in your case, AnyLogic wanted us to prettify our models at the point, and Jeff also is a master, which I thought was to kind of be complete. So we just loaded this in. This situation is going to depict a situation where we have system dynamics driving agent evolution. Not exclusively. This doesn't mean you have to commit agents are only using system dynamics or only using state charts. Far from it. Just each individual will have at least some components associated with characterized using system dynamics. But what is system dynamics stocks and flows being used for here? It's being used to capture the dynamics of continuous quantities associated with that agent. And again, I've mentioned it before, so I won't belabor too much. Things like weight, things like immune strength, or immune level of immune memory, which is a dynamic quantity. Things such as the level of risk perception, things such as emotional, level of anger or emotional arousal. These are things that could be captured using stocks and flows. They're continuous quantities that exhibit plausibly continuous dynamics. Continuous in the sense that they increase and decrease in a continuous fashion. And particularly where we have feedbacks, ladies and gentlemen, cases where my emotional state is coupled with that of my child, and if the child gets upset, it'll affect my emotional state, and vice versa. My emotional state will come out in terms of the child's emotional state, or where we have coupling of pathogens from one person to the other. Or attitudes or strength of belief in something. We have knowledge attitudes, and we have norms between people. My sense of whether it's appropriate to use an e-cigarette, in my workplace may depend on the number of other people who are using it around, et cetera, whether I want to try it, or for breastfeeding, level of perceived support for that. So here we have regulatory processes that may be operating, or in fact, reinforcing processes, things like vicious cycles and virtuous cycles. And there's no language that I know that's more expressive for this than system dynamics and stocks and flows. I mean, it's just, system dynamics centers around accumulation and feedback processes. And it's just a beautiful language for describing those situations where you have continuous dynamics that exhibit these sort of regulatory components. Frankly speaking, I don't think the mainstream agent-based modeling literature has really, I don't think it's really grokked feedback in the way the system dynamics world has. And there's a lot of compelling psychological, physiological processes where feedback is absolutely central, and where agent-based models often do a pretty poor job. They have richness in other areas, but they're poor in terms of this adaptive behavior that has real feedback associated with it. And often their continuous dynamics is very simplistic. You know, once a tick, you update this by multiplying by this variable, and there's very little in the way of rich feedback or accumulation. So it's a very powerful idea. Incorporate continuous feedback in the form of stocks and flows when you need it. You may still have other variables that are continuous which you don't use stocks and flows, but these are a very nice language. And indeed, there's a lot of theory from physiological literature, from the likes of Guyton and so on, to characterizations even of some psychological dynamics. There's theory behind it. And you saw Kurt talk some about that. Kurt just finished somewhere between 75 to 80 paper review of sort of the literature on modeling of human behavior, particularly related to substance use and so on. And there's, when you come to theory, there's a really nice way to capture a lot of theory out there, a lot of theory that's published already as differential equations or close relatives that you can incorporate physiologically and to a certain degree psychologically. You could translate things. It's declaratively specified. We can put this down. There's not a lot of programming involved in it. It's continuous time. It's very nice. Very nice, straightforward model. So we started this back almost 10 years ago with some of our work with infectious disease dynamics, translating work that had been the focus of laboratory studies into what we called immunoepidemiological models. And we have a series of said models that we created, everything from H1N1 flu to chlamydia to more sort of mouse-borne viruses. We have depictions, and these are based on immunological knowledge bases in experimentation. And just to give you a very brief depiction, this is one of our earliest little models where we had, and this is based on a really delightful work. I don't know how many of you are familiar with Anderson and May's foundational textbook on infectious diseases of humans. It's kind of the Bible for mathematical epidemiology. Maybe that's a bit overstating it because it's getting kind of old, but it's the seminal work in that area. I mean, it's amazing work. Infectious Diseases of Humans by Robert May and Anderson, Roy Anderson. It turns out May went on to start modeling at the immune level, and so we took some of the models that came out of that work. He and Dominic Wadars and a set of and Nowak created these sort of models, and so we translated some of them in an immunoepidemiological context. So here we have viruses, we have individuals whose cells can be uninfected or infected, and infected cells can die by attack from the immune system, and the immune memory is represented here by a state variable Z or Z, and these cytotoxic T lymphocytes, represented by Z, they can kill off infected cells. There's also some natural cell death. This is a very coarse-grained depiction of the immune system. Yes, it could be depicted at an agent-based level, but remember, when it comes to the world, there's no bottom. So it's hard to hard to argue that you always need to go, further down to get accurate results. And mathematical immunologists have achieved great success in using models like this to sort of characterize dynamics of a lot of basic dynamics associated with the immune system. So this virus, these free virions, these virus particles, they infect uninfected cells. And there's dynamics associated with them as well that are often quicker than with the buildup of infected cells. These free virions, importantly, and this is the key immunoepi linkage, these free virions come not only from multiplication within an individual, but they also come critically from other individuals nearby. So you notice there's virions for neighbors. We have here omega times total viral load of neighbors. Total viral load of neighbors is a function which simply goes over each neighbor and totals up the viral load from those neighbors. So the idea is that if you have neighbors around with whom you are sharing, say, needles for intravenous drug use, those neighbors, you'll be exposed to some virions from those neighbors. Now, it turns out that the exact formulation here, whether it's continuous or discrete, we played around, doesn't seem to matter that much, because what happens is, as long as you're exposed to a small bit of viral load, what determines it after that is your immune strength and so on. It's the endogenous dynamics. So whether you're exposed to more or less is not really the issue, because this contribution from neighbors is extremely small. The point is it gets some into your body of HIV, or some into your body of H1N1, or some into your body of chlamydia, and after that it's an endogenous dynamics. It's a dynamics that's associated with your level of immune activation and critically your immune strength. We were very interested for some of our work in looking at the impacts of different levels of immune system strength in the population as it mediated spread of infection. So you think about something like H1N1. In the summers, you think about seasonal flu. H1N1 in the summers here doesn't disappear entirely. It doesn't merely go to Australia and New Zealand and live there in the summer here, winter there, and then come back from travelers. I'm not responsible for bringing flu to Australia. When I fly there in the spring. Instead, what goes on is it often lives in people who have lower immune system strength, those who are in nursing homes and are elderly, those who are taking immunosuppressant drugs, those whose immune systems are weak because of the depredations of age or chronic disease such as diabetes, which is has adverse immune impact, etc., and BFO risk factors like smoking, intravenous drug use. So in those people, you can often get virus clustering because they have a weaker immune system strength, and that affects all of their their likelihood of getting infected in the first place, the time that they're latent, the time that they use to clear the infection, their risk of dying. So we were interested in a heterogeneous population, heterogeneous in terms of immune system strength. What would the impact be on the spread of infection in that community? We were also interested in the ways in which this sort of system, this kind of private, it's not private, individual health system within you that preserves your health, individual health system rather than public health system, how does that interact with the public health system? So if we, for example, lower your exposure to certain pathogens in the broader population, let's say chickenpox, to what degree would that predispose you to worse reactions when you get exposed to chickenpox in terms of your level of infection and viral load? So those were some of the questions. We weren't actually looking at chickenpox in particular, but the basic idea is that your immune system has defenses, and if you start depriving it of opportunities to see pathogens occasionally, it may be that the immune memory decays to such low levels that when you are hit badly, rather than getting boosted periodically in your immune system strength by small exposures. That was part of what we were examining, ladies and gentlemen, using these sort of models. So let's just take a look at this. I don't have time to go into it, but let's look at beta-viral. We presented immunologist who sadly has passed away now, Benny Sahai, who was at Cadden Provincial Labs in Winnipeg. I just ran it with high fatal viral. I should have told you. Sorry, folks, for the discombobulated lectures here. One feature I didn't notice. Individuals. This is in person, right? We have these stocks and flows. But beyond that, over here to the left, we have a state chart, and the state chart has a type of transition out with which we've enjoyed no previous experience, at least in this boot camp. This is a transition out which is associated with a condition, and this is the condition here. And what this is saying is, if my viral threshold, if my viral level, that value of that stock, exceeds a fatal viral level threshold, then I will die. Okay? See the idea? And indeed, Benny was talking to us about that with flu, that for very elderly individuals, there is a risk that beset by seasonal flu, because of their poor immune system strength, they may succumb to something that would be brushed off by someone younger, a seasonal flu infection. There's the king. Okay. Okay. So I'm going to run this and going to and what we're going to see is that there's an index individual who gets infected, and from that person, a set of nearby individuals get infected. Let me describe the purpose of this animation, or the semiotics of the depiction. So, ladies and gentlemen, the redness depicts their level of viral load. The width of the circle depicts the level of CTL activation. Okay, the sort of number of the level of immune strength. Okay. Okay, so ladies and gentlemen, you can see this infection spreading from one person to the next in the population, and you can see their immune dynamics illustrated, right? Their immune dynamics here associated with these state variables as captured with system. So their immune system is responding to this, and responding in a way that that leads them to develop defenses. So we could go down to the level of and we could look at this person's history of viral load, and you can see they're being exposed and it's coming down. We can also look at their level of immune activation and immune memory, and we can see that that's going through sort of cycles as well, where it builds due to exposure, comes down, etc. Okay? Okay, ladies and gentlemen, so this is a model of dynamics characterized by stocks and flows. I'd like to open another one up here, and this is called gridded system dynamics V8. Okay, that's version 8. Oh man, we're gonna have to take another vote on something. I forgot. Best practices, Jeff. So please open up gridded system dynamics V8. Okay. So if you open that, you'll see another model, which agents which exhibit continuous dynamics characterized by stocks and flows. So we're going to open this up. Here we are, gridded hybrid model. I'm going to close these others. Close others. Save those. Boom, boom, boom. Okay. Okay, ladies and gentlemen, we're going to run here. Okay. Okay. Let's run this gridded hybrid model. Okay. Here we have a set of patches. If we go down here to the patch level, we'll see that each patch is characterized according to immature and mature organisms. Okay? And as we run this, we'll see that there's some dynamics associated with it. Basically, each patch communicates with its neighbors. So these organisms move from one patch to the other. One of the things which motivated this sort of modeling, one of the projects was a sea lice project, which a student in the camp brought a few years ago, where basically you'd have patches of ocean or patches of water, and you could have these sea lice that would breed in each patch, and they'd move to neighboring areas. But you imagine similar things for spread of mosquitoes that are affected by West Nile virus or affected by Zika virus from one area to the next. So basically we have dynamics within each patch characterized using system dynamics, and then there's a couple of different patches according to some immigration, for example, occur from one patch to the next. Okay, I won't go into this, but this is kind of a spatially rather than a topologically situated model. Okay, continuing on briefly, we're going to open up a model now, also related, but which also relates to a later category. Well, maybe we'll go into the next one, then we'll come back to that later category. So next one, agents drive aggregate system dynamics. What I'd like to show you here, and we'll finish up these next two quickly, is I'd like to show you one that is called here Basic Health Economics, ABM, Any Logic 7. Okay, here we go. Basic Health Economics, ABM, Any Logic 7. Do you see that? Okay, see or not? Good. Okay, ladies and gentlemen. Okay, so let's look at this model. So here we have a model. We have individuals who are characterized, persons in this model who are characterized as being subject to a state of progression of conditions related to diabetes, dysglycemia, including complications involving end-stage renal disease and transplants. Okay, and here, associated with each state, we have a quality of life measure and a cost per year measure. Importantly, ladies and gentlemen, let's go click on one of those states. Go click on, for example, normal glycemic. Here we have cost per year computed as 0, and we're assuming we're taking diabetes costs into account, and quality of life equals 1. Let's look at type 2 diabetes. We have quality of life equals 0.8, so that's some health-related quality of life measure, perhaps a utility-based measure, such as from the Health Utilities Index. And then we have a cost per year associated with being in that state. Okay? Now, end-stage renal disease is a higher cost yet, associated with dialysis. And then you'll notice that there's an event called that brings one into the transplant state, okay? And you notice here we directly increase the costs accumulated by something, by $75,000, for example, okay? And we increase the undiscounted cost too. Let's go over to Maine, since these are in Maine. Let's go look at Maine. Ladies and gentlemen, let's go down Maine. Okay, so if we go to Maine, what we'll see is that there are these quantities accumulated. So there's a population of people, to be sure. And in fact, there's statistics computed on that population, such as cumulative cost, quality of life, cost per year, count of non-diabetics, count of pre-diabetics, okay? And then you'll notice that when it comes to QALYs, for example, there's new QALYs per year, which calls off to this. What do you think this is, ladies and gentlemen? What's this cumulative QOL? What do you think that is? I'm calling it a population. It's a statistic. So if we go to population here, we'll find cumulative QL. It's actually cumulative across the population. It's a sum up across the population, a sum across the population of quality of life. And this cumulative QOL is then, so that's sort of the sum up of quality of life across the population. And if we're summing it up across the population, it's basically the count of people in the population weighted by their quality of life, each of their quality of lives. And then we're putting this, having it flow into quality adjusted life years. Ladies and gentlemen, when you have a flow into a stock, a single flow, that stock is the integral of this flow. Let me repeat that again. At a mathematical level, this stock is the integral of this flow. Why? Because this flow represents the rate of change of this stock. Okay? And mathematically, if this represents the rate of change, and this is this is going to over time be accumulating, be integrating up that rate of change. You could think of this as a sum of these on a per day basis almost. Take into account the fact that each day is very short. It's summing this up. It's summing up the qualities per year. Similarly, over here, just to the right, we are totaling up costs. We have some new costs, some rate of spending. Okay, it's $2,000 a year for someone who has diabetes, and that's accumulating into this across the entire population. So we're taking across the entire population the new cost per year. For this diabetic, it's $2,000 a year. For this person, there's normal glycemic, it's $0 per year. For this person with end-stage renal disease and on dialysis, it's $50,000 a year. We're totaling that up to over all the years to arrive at accumulated undiscounted costs. In short, ladies and gentlemen, and I'm not going to belabor this more because time is of the essence, these quantities here represent summaries up of what's going on at an individual level. They're computing these basic health economics quantities like accumulated quality adjusted life years lived or costs spent, in case either discounted or undiscounted. So we can this model, and what we will see is that there is a population of people, 993 people right now, but we have them accumulating up quality adjusted life years as that population is living. Here's qualities lived. I don't have to create that. I could simply do this. Okay. Great. So here we have quality adjusted life years lived. Here we have life years lived. Here we have costs, etc. And this is all reflecting a state of a population which is exhibiting changes between different states. Okay. So there we have a situation where agents drive aggregate system dynamics. Okay. Next, we're going to go down to this last one. Aggregate system dynamics drives agent population evolution. Let's open that model. That will be our last one. Okay, I'm going to close this. And we're going to open up a model. It calls something like environmental reservoirs or environmental contamination. Okay, hybrid models. And it's called environmental contamination hybrid. Okay. So open that up. Okay. So ladies and gentlemen, what we see in this model in Maine is a set of populations, once again, a population of people. Ladies and gentlemen, a population of homes, a population of workplaces. Now, each person here, if you click on person, will have an infection state chart, which terminates in recovery. And then they'll have a depiction of how they're spending their time, off time or work time. And they go to work and go home. Now, what do you think is going to happen at go to work? What do you think we'll do? We'll move them to the destination. When they go home, we'll move them to their home. Okay? Move them home. You notice they work for 8 hours and they're at home for 16 hours. Very simple representation. Okay, ladies and gentlemen, let's go look at workplace. So we're going to open up workplace, and we see something distinct. We see something we haven't seen before. The workplace has associated with it. It's serving many people, but associated with the workplace is a pathogen reservoir, which is keeping track of the amount of pathogen present on the surfaces of that workplace. Now, that's admittedly a very crude aggregate depiction, but we could have this for different areas of the workplace. And in fact, we have versions of this model of long-term care facilities where we'll have these pathogen reservoirs at many places throughout the long-term care facility, different pathogen reservoir. The key point here, ladies and gentlemen, is that we have dynamics of pathogen reservoirs accumulating at this workplace. You could imagine a similar model for cholera, where you have some bodies of water, and there's high and low virulence levels of sort of cholera microorganisms there, and there's dynamics associated with that based on the weather and the temperature and the influx of cholera. So let's look at this. The outflow here is very simple. We have a mean pathogen lifetime, and we have some pathogen inactivation. It's simply a first-order delay. Pathogen reservoir divided by mean pathogen lifetime. By contrast, ladies and gentlemen, here, for shedding of pathogen, this is where it gets particularly interesting. For the inflow, they have a per capita shedding rate times some number that's based on the number of infective people who are within range. We're counting the number of infected people who are in range. In other words, the number of people here right now who are infective, each of them is shedding at a per capita shedding rate. So there's some set of infective people, and each, maybe it's 0, maybe it's 1, maybe it's 2, and each of them is shedding at a certain rate, and hence our pathogen reservoir is building up at that rate. Now, let's go look at the home. Home is where the hearth is. Home is where the heart is. Let's see what else, ladies and gentlemen, lies at the home. So if you click on home, you will see a pathogen reservoir even yet at the home. And this is representing, a level of potential environmental exposure that a person might get at the home. Do you see that? So when a person goes back and forth between home and workplace, if they're infective, they may get sick initially at the workplace, then they bring it home, and they start to bring up pathogen there. And other people who cohabit that home with them may be exposed, ladies and gentlemen, to pathogen. And by virtue of being exposed to pathogen, what will happen? Let's go back to person, circle back once again, because there is a point that I glossed over. Indeed, a point of significance in this model. You note environmental infection here within the state chart of the person? That is based on a rate. And whence does that rate come? It comes, ladies and gentlemen, based on some coefficient, some sort of infection hazard per unit exposure times the current exposure level. And whence does that come? The current exposure level. Basically, ladies and gentlemen, if you check this out, it's taking into account the reservoirs, whatever location they're at. If they're at home, it uses the home reservoir. If they're at work, it uses the work reservoir. I wouldn't do this for many models which have many locations. There's going to be a more elegant way to do it there. But the point is, wherever they are, they're exposed to that pathogen reservoir. Okay? And that imposes a hazard rate of infection, a risk that they'll get infected at that location. So, ladies and gentlemen, we have a sort of organic unity to it. So there's persons, they can get infected, they can reach a shedding state, and when they shed, they're shedding into the pathogen reservoirs at their location. But a person who's susceptible can be exposed to those pathogen reservoirs, contract the infection, and reach a shedding state themselves. Okay? So let's run this thing. Let's run it with a small population. Okay. Okay, here we go. Okay, so here we have, oh, this is a tiny population, man. That's less interesting, but we can run it. Okay, so we have people. You notice they're getting. In fact, here we have 2 sick people. Now both have recovered, and now if we were to go look at let's look at the workplace, and I'm going to go look at the dynamics. It was high and now it went low. Let's do it with a bigger population. Let's look at a medium, say medium small population. I should be more expressive in my. Okay. Okay. Here we go. Here's a population. Notice all these people. There's one person starting infected. What do you think is going to happen with that person who's starting infected? Are they alone going to remain infected, or what's going to happen? Okay, they're going back and forth to work, right? Now we notice that their home of that person is getting increasingly building up pathogen. Do you see that on the screen? This one, okay, but they've infected some people at their workplace. They're clustering at workplaces and then going back home. People are going into work and now going back home. Boom. And they're bringing the pathogen back and forth. And we have homes beset by different levels of pathogen. This home is yet spared from the worst ravages, but several homes are highly burdened. Okay, and these individuals are uniformly appear shedding right now. So the outbreak is at its worst, and if we continue to run out, people are recovering, and now the infection levels associated with workplaces. Notice these are becoming smaller. The infection has passed behind us, and you'll see the pathogens in workplaces. So a little model showing kind of workplace pathogen reservoirs, home pathogen reservoirs, and indeed it could be readily extended to be schools or other locations as well. Okay? So that, ladies and gentlemen, is the last of this. Here, the aggregate system dynamics, say for a workplace, can infect an individual, and that individual can ultimately affect the workplace. We could have similar things. For example, in a West Nile model, we might have mosquitoes biting people that are represented as agents to capture effects of their particular decision making with respect to exposure. We might characterize them as situated agents making decisions in the workplace. Okay. I think I'll leave this in terms of because we have limited time modeling, and I would argue that what you can gain from combining the elements there is greater than you can get from either element in isolation, and maybe more than you can get from each of them taken in isolation added together. Rather you get something where the whole may be greater than the sum of the parts. You take into account, ladies and gentlemen, the considerations of the model building process, learning along the way, and being able to expand the model at key points to take into account extra levels of detail, or to fill in and no longer have certain detail for certain regions of the model. Models are, as Jeff says,